would like to welcome everyone back today to the workshop, day 2 of the workshop on bionic arms. To start off with, I would like to remind everyone attending about a few pointers. So first off, it is regarding posting questions. So there will be separate Q&A sessions after each session. But if you have any questions during each session, you can post it in the chat box, and the moderators will direct it towards the respective speakers, and it will be addressed during the Q&A sessions. And there will be a link to provide your feedback regarding our workshop today, and please keep in mind to fill that out as well. And the other reminder is regarding the challenge that has been posted yesterday as well. I would like to show your direct attention towards that as well. Okay. So this is the challenge. As you can see, the link is given here. We will be posting that in the meeting chat as well. You can upload your completed challenges to the link that is given. So the task is to design a functional finger prosthesis, and the background is as given here. The middle finger has been amputated near the metacarpal level following an acute injury of a 35-year-old male fitting the 50th percentile male population in Sri Lanka. The amputee is by profession a carpenter and mainly rely on the dexterity of his hand during woodworking. The amputee hopes to use the finger prosthesis for both domestic and trade-related activities of his daily life. So the deliverables or the core of your challenge would be to prepare graphical representation of the design through freehand sketches with labels or CAD models. And you will have to explain the working mechanism of the finger prosthesis, including the details of the mechanical and the controlling hardware, and describe the considerations for developing the proposed finger prosthesis. And the instructions are as you can see in the screen. The participants will be given 2 weeks to complete the challenge. Once the assignment is completed, you will have to upload the assignments to a Google Drive. The link will be posted in the chat as well, and share the link or the Google Drive folder where your assignment is by completing the form. The form link would also be uploaded to the chat. And the prize would be this. It's an educational kit, the Inspire 1.0. So the winner of this challenge would be receiving the Inspire 1.0 educational kit. Okay. So today, to start off, I would like to first introduce our the Q&A coordinator, Engineer Kitmi Vidanage. She will be moderating the Q&A sessions. And we can move on to the speakers for today. So our first speaker today is Dr. Sanjay Bandara. He received his BSc Honours degree in Engineering in 2010 and his MPhil degree in Mechanical Engineering in 2015 from the University of Moratuwa in Sri Lanka, and the PhD degree in Mechanical Engineering from Kyushu University, Fukuoka, Japan in 2018. He was previously a lecturer in the Department of Mechanical Engineering, University of Moratuwa, and a postdoctoral fellow at the Systems Engineering Laboratory of Kyushu University, Japan. Currently, he is an assistant professor with the Advanced Medical Devices Laboratory at the Department of Medical Engineering in Kyushu University, Japan. He is an associate member of the Institute of Engineers Sri Lanka and a member of IEEE. His research interests include wearable robotics, surgical robotics, and brain-computer interfaces. So, Dr. Sanjay Bandara, over to you.
Thank you, Mr. Pasindu. So let me share my screen. Right, so again, thank you very much for the kind introduction. So first of all, I'd like to start by saying thank you for organizing this amazing event. So back in 2010, 2011, I remember I was the first student in the Bionics laboratory in the University of Moratuwa with Professor Gopura. So by that time, like we had hard times finding some enthusiastic people who are encouraged or who are motivated on the Bionic limbs. But I saw like yesterday, there were many students and many participants from different backgrounds have grown interest on the Bionic limbs and knowing more about them. So I think for the last 12 years, Sri Lanka has done good in this area, and I think it's in the way forward. This is a very nice start for the future generation. And I'm very glad to be here today, also joining with you guys, sharing some of my knowledge acquired through the last 12 years. So currently, I'm an assistant professor at the Department of Mechanical Engineering of University of Kyushu University, Japan. In the background, you can see the Kyushu University. We are the largest campus in Japan. So moving on to the presentation, first let's have a brief recap on what we discussed yesterday. So mainly the topic of the workshop series is the bionic limbs, and mainly two types as introduced by Professor Gopura yesterday, the prosthesis and the exoskeletons. The prosthesis, they act as a replacement to a lost limb, and their mechanical complexity depend on the anatomy, the number of motions to replace, the number of degrees of freedom, and the controlling complexity also varies depending on the type of amputation. So for this kind of devices, intuitive controlling is necessary for user acceptance. And in the exoskeletons, they act as a supplement to an existing limb, and they can be used for rehabilitation and power augmentation mainly. Their mechanical complexity also depends on the anatomy and the number of motions to support it, for example. And the controlling complexity varies depending on the number of motions to support and the health condition of the wearer. Intuitive controlling is again necessary for the user acceptance. So this was what we discussed yesterday from Professor Gopura and from Engineer Pubudu. And so moving on to the today's topic, muscles for communication, muscle signal-based control of bionic limbs. So what is communication? Communication is conveying a message from one place to the another place. And importantly, when we healthy persons communicate, we use basically for basic communication as I'm talking right now. But inside the body, there is a different mechanism developed for these communications. So mainly, if a person has lost his limb, then if he wears a prosthetic, for example, then how do we connect this link between the already available mechanism of the human and also this link to the human or the prosthetic limb that is worn by the amputee? So this is this will be the main topic of today's talks by myself and Dr. Tilina. So let's, for example, let's assume now you in this figure you can see a transhumeral amputee and also who has lost his arm above elbow, and a transfemoral amputee who has lost his knee, who has lost his leg above knee. So if he wears this prosthetic leg, or if he wears this prosthetic arm, how can he convey his thoughts? For example, for grasping something or for walking, how can he convey this message? This is what we are going to talk about today. So for this purpose, in the human body, as I mentioned, we have the neuromuscular system. So the neuromuscular system consists of the brain, the central nervous system, and the muscles. This neuromuscular system contains the information from the motor neurons in the brain that is generated the motion intention, which is what motion needs to be done is the motion intention. This is generated in the brain at the motor neurons, the motor cortex. This motor cortex will transfer these motor signals to the upper motor neurons, to the central nervous system, and then through the lower motor neurons to the muscles. So if we can intercept at any of these points, for example, if we can intercept in the brain, we can intercept in the muscle, we may be able to understand what kind of motion the user wants to do. So in today's talk, Professor Dr. Thilina will be focusing on intercepting with the human brain, and my focus will be on intercepting this muscle signal pathway at the muscle. So there are different kinds of muscle signal measuring techniques: electromyography, the mechanomyography, and EMG stands for electromyography, HD high density electromyography, and targeted muscle renovation. This is also a kind of EMG technique, but which involves some surgical procedure. So I will be introducing all these four things today, and also I hope at the end of this talk you will have some kind of idea how we can convey these brain thoughts to the prosthetic limb or the prosthetic or the exoskeleton that the patient or you are wearing, as a muscle as the intermediate communicator in between the brain and the limb, artificial bionic limb that you are wearing. So how to successfully and efficiently decode this several simultaneous motion intention of human for robotic related applications, let's talk. So electromyography measures the muscle response or the electrical activity in response to a nerve's stimulation of the muscle. So there are two types, surface EMG and the intramuscular EMG. Surface EMG, as the name suggests, is measured from the surface of the muscle. You can measure it from the surface of the muscle. And one of the limitations is only limited to the superficial muscles, which means the top layer of muscles. There are muscles in the inner layer of human limb as well. So we cannot access to the inner layer of muscles with surface EMG. This is one of the limitations. And we use we measure the now if you consider this limb, this muscle, we have to place the electrodes in the belly of the muscle. This is a long muscle, and we have to place the electrodes in the belly of the muscle because we are measuring the potential difference in this muscle at two locations. We have to measure the potential difference. In the intramuscular EMG, so we measure this using a needle electrode, which will be inserted through the muscle. So with this, we can measure the inner EMG signal from the inner layer. So, but this is invasive. So different types of electrodes are available depending on the application. So it may be again 2 electrodes inserted, but sometimes it may be only single electrode inserted into the muscle for the measuring. So this is EMG. Then we have mechanomyogram, MMG. So this is a mechanical signal observable from the surface of a muscle and measures the low frequency vibration that may be observed when a muscle is contracted. So for example, when we close our hand, some part of the muscles over here you can feel they are contracted and then released. So it generates a kind of frequency. So we can measure this frequency of vibration using an accelerometer or simply a microphone placed on the skin over again in the belly of the muscle. So one advantage is we can use this to measure muscle activity from the deeper layer of the muscles. But maybe we need some kind of differentiation techniques, like how to identify. But we can measure, so without invasive techniques in the deep layer. And we have the high density EMG. This high density EMG is a measurement of EMG signal, but now, as I mentioned earlier, in EMG we only place one electrode in one muscle. But with HD EMG, as you can see here in this figure, we place the electrode array like here. So around here we have like 192 channels of electrodes measuring EMG from the top surface of the muscle. One advantage is now through like some kind of source separation techniques, we can try to identify the motor unit activities, the motor unit behavior using these HD EMG signals. They are advantageous because they are not contaminated by some brain activations related to the different body tasks also, and also the environmental noise. And then we have targeted muscle renovation. So this involves surgical procedure. This is developed to increase the number of physiologically appropriate control inputs available for use with the prosthetic device. So if we know, like if some person has lost his limb, the number of muscle sites that we can measure the number of the EMG is reduced. So as a solution, what we do, we take some of these, now for example, these finger motions are controlled at some part of muscles around here. So this, as I mentioned earlier, all these signals will be coming through the brain, through the hand to the distal area of the proximal area of the forearm. But if some person has lost his limb here, his neurons carrying these signals will be stopped here. So what we can do, we can de-innervate these neurons and then re-innervate it at these electrodes at some part of the body where we don't use much. For example, the chest muscles. We don't use these chest muscles a lot. So we can surgically change the muscle direction, muscle path to the chest. And then we can measure EMG from the chest muscles, for example, to understand the motion intention. So let's see this video. Wait.
The muscle, when you're making those muscle contractions, they emit electrical activity. Mm-hmm. Kind of like a radio emits music. Same thing. You can turn the radio up and it can be louder. You turn it down, it's quieter. This technology is like listening to a radio. Sorry, the technology that is I don't want to call it old, but the conventional stuff.
So now you can see in this person, if he is a transhumeral activity, the median and distal radial nerves, which runs through to the upper limb, to the forearm, has been reinnervated around here, and then it has been controlled to measure to control the open and close of this prosthetic hand.
Close, relax, open, relax, close.
I'm just tensing it up. I can feel it just.
That's okay. Now try this for me. I know we didn't train the system doing it lighter, but I want you to try that. Close it just a little bit lighter, not squeeze it too hard. Okay. There you go. Okay. And open a little bit lighter. Great.
Great. So for the sake of time, I think I already am in the
fast
middle of
load,
time.
Yeah,
I'm already running late. So I will move forward. Now next, let's talk about, in today's topic, we only talk about EMG, like surface EMG, because this is invasive and this is easily available, and this can be used easily for this purpose. And this is commonly used by a lot of researchers, and also in some of the commercially available systems. So we'll be talking about surface EMG. First, we need to record. I saw a question yesterday how to measure this kind of muscle activities. So this is the signal measurement techniques. First, we need the human muscle, of course. And then we use some kind of electrodes like this. In this case, these are wet gel pads, which I will be shown in few seconds how we have to attach on our forearm. And then this is the signal cable from the electrodes to the input box. So in this case, which I'm showing you today, the transmitter and the both input box contains the amplifier and the input box. Then in this system today, what I'm showing you, it wirelessly transfers these EMG signals to a receiver which is connected to the computer. So this is the this is the cable for EMG transmission, this part. This is the electrode pads. This is the transmitter. This is the receiver. So first, we need to clean the skin with some alcohol, maybe, and then we will place the electrode gel pads. And then we will connect the electrodes like this. So the muscle activity is measured with reference to a neutral point. For example, the elbow. In the elbow, there is no muscle activity. So we connect the reference electrodes to the elbow, and then we measure. I'm going to show you two kind of muscle activations today. In these electrodes are connected like this. So these are wet electrodes. There are also kind of electrodes, dry electrodes. I think University of Moratuwa has this kind of EMG amplifier, different sub brand. Then we switch on this transmitter and the receiver, and they get paired. Then we can measure this from the computer. So this is one example how EMG looks like. Now this first top layer is for the closing, and the second layer of EMG is for the opening of hand. So you can see how it happens. So it's almost real time. Okay, so now decoding. Now we measured, we recorded the EMG. Then how do we identify the motion intention with this EMG? Is the next question. So basically we have another three more steps: the data segmentation, feature extraction, and classification. In the data segmentation, we mainly have two types: the disjoint segmentation and overlapping segmentation. So this how we segment data into time windows is important, because the EMG data contains information from temporal information, which we need to enhance. So we should be very careful that we will not destroy the containing information. And also then this will be then next step will be the feature extraction. We have three types of features, mainly the time domain, frequency domain, and time frequency domain. In the time domain features, we are interested about the time series data contained inside EMG signal. In the frequency domain, so this EMG you saw in the signal, like they have some kind of frequency inside. This this is internally changing. So we are also interested about this kind of information. And lastly, the time frequency domain, which we can get information from the both related to the time series and the frequency changes. Then we will forward this extracted features to the classification technique. Now this is using machine learning. So for example, we can use neural networks, which is kind of similar, kind of black box, similar to how we understand in the human brain, which is in our neural system, or fuzzy logic, for example. And also recently there are some kind of deep learning techniques as well developed to understand this kind of human intentions. So next I will show you a couple of projects that we were working on. So this is a hand rehabilitation robot developed in Kyushu University. This is mainly used for hand rehabilitation, hand close and open. As you can see here, this is based on a soft mechanism like springs. So I don't think I have the mechanism here. So we push one layer of springs with this motor, or as you can see, one linear motor. So this will bend the fingers of the hand robot. And we only have one motor to control. I heard, like in yesterday's presentation, Mr. Pugudu was talking about the underactuation. So this is underactuated. It is important because in a prosthetic hand or exoskeleton needs to be lightweight. Okay, so this is the EMG controlling. As you can see, now the EMG sensors are connected to the other hand of the human, and when he performs the hand open close, the robot moves. So this robot, we are currently in the commercialization steps. So you can see how it looks in real life. So especially after a stroke, the people, most of people lost their hands function. So this robot can be used for this purpose. Though this is not a prosthetic, as you discussed yesterday. Right. So now one of the main problems, as I said, is understanding the motion intention of the patients, because as we healthy subjects, we have the whole muscle activity, but the patients have very less muscle activity. Like it may be even zero. Like sometimes we even can't see a muscle activity. So in this case, we have to use some kind of, since this is a single degree of freedom robot, the controlling is pretty straightforward for healthy subjects. Though there are some kind of problems like the muscle fatigue or maybe muscle crosstalk between these two muscles. But when it comes to patient, it is very important how to understand the motion intention of the patients, because they have almost no muscle activity. Of course, depending on how their brainstorm state. But what we do now here is we record the raw EMG data, and then we apply. Now, as I mentioned earlier, we have 4 steps: EMG acquisition, and this data segmentation. As I remember, we have 60 millisecond windows of data segmentations. And then we derive the time series information using average rectified value, ARV. And then we use support vector machine to train a model, which we will use with the timestamps of the grasp and closing. Open and closing of the hand. Then we use this learned model in the prediction phase again to control this hand in real time. So when we use machine learning, we have two steps, like the learning phase and the prediction phase. So let me show you a video. Now this is with machine learning. Now we call this is extension, this is flexion, this is relax. Right, so this is the actual control of the robot. Okay, so let me move forward quickly. Now, next I will introduce you a control of transhumeral processes. So I think you are familiar with this term, the transhumeral. This is the humerus bone. So we have the amputated in between the elbow and the shoulder at the humerus bone. So we call it transhumeral amputation. So transhumeral amputee can use a transhumeral prosthesis. So only for transhumeral amputee, we have this biceps and triceps muscles. No any other distal muscles are available to control the this transhumeral prosthesis. So what this was done in Saga University, and what they did to control the elbow motion, which is I think is straightforward because we already have the muscle. So when we do elbow flexion extension, the biceps and the triceps are involved. So this can be directly done using the biceps and triceps. But also they use they use this biceps and triceps to control the hand function. So the hand grasp is controlled using the two contractions of the elbow, sorry, the biceps and triceps together. So now when we flex and extend the elbow, only one muscle is activated at one time. But in this algorithm, when the both muscles are activated together, the hand is open. And when these muscles are relaxed, the hand is closed. So this is how they did the control using a fuzzy controller. So this is again another project done at the University of Moratuwa. Thank you very much, Professor Gopura, for the video. So this is a 3 degree of freedom lower limb prosthetic, the transtibial prosthesis. Now, as I said, this is a dry electrode, which they are using. So I said there are two types, like the wet and the dry type. They are using a dry type of electrode in this case. Right. So, and this is, again, I got the video from the Professor Gopura. So this is, again, done in Saga University. This is a exoskeleton robot. It is employed with the fuzzy neuro architecture, and it can provide the adaptive nonlinear control of the exoskeleton because EMG signals, they vary with the factors like the physical and the physiological condition. And also it is important where we place the electrodes and the placement, the shift of the electrodes. So this is highly nonlinear behavior of EMG. So they use fuzzy neuro architecture, the fuzzy with the neural networks to control this robot. So this is the supination pronation motion. This is the wrist flexion extension motion. Okay, so yeah, it's almost time. But before we wind up, so I don't want you to stop like learning only at this point. So as I said, this is a good starting point for you to start on developing control systems, or maybe like, for example, you have a design challenge, and then you can extend this design challenge into something that is workable using EMG. So this is, I copied from YouTube. So thank you very much for the original creator. So I'm just showing you what is available, and of course, I think you know how to do searching, maybe even better than me. So you can go and
let's see the Myoware EMG muscle sensor kit that I recently purchased from Amazon. So here are the multiple packets containing the main sensor board along with the expander board and different kits. We will see all the packets separately and learn what is inside and how to use them. So this is the first board called Myoware Muscle Sensor, or the Embedded Electrode Connectors. The Myoware Muscle Sensor is an all-in-one electromyography sensor from Advanced Technologies. The Myoware board acts by measuring the filtered and rectified electrical activity of a muscle. It gives output from 0 to V in volt depending on the amount of activity in the selected muscle. There are a few audio amplifier IC on the board. An audio amplifier is used so the activity can be heard. EMG measures the electrical activity of a muscle during rest, slight contraction, and forceful contraction. Muscle tissue does not normally produce electrical signals during rest. When an electrode is placed, a brief period of activity can be seen on the oscilloscope. You can see it has 9 pins as R, E, and W pins. On the right, it has a signal, minus, and plus pins. On the left, it has ground, SHID, or power pin, and raw pin, which is also a signal pin. There is also a small potentiometer for controlling the gain. Well, on the backside, there are connectors for 2 electrode pads. So as explained earlier, the R, E, M pins are the mid muscle, end muscle, and reference electrode pin. To learn more about these board parts, visit the link in the description. Now let's see this packet. So this is a Myoware cable shield that comes along with this kit. It is optional. First, let's see the Myoware EMG muscle. Now let's just see this packet again. This is a Myoware power shield. The Myoware power shield is designed to take 2 coin cell batteries such as some standard CR2032s. They are connected in parallel for extended capacity at a nominal 3.0 volt. This shield also feeds directly to the Myoware muscle sensor. And inside this packet, there is an electrode cable. The cable has 3 electrodes. Both sets of contacts will be connected together, so make sure to only use one pad for each reference R, end E, and middle M pin. Just insert the 3.5 mm audio jack to this connector. These are the pads that come along with this kit. I have a total of 6 pads here that I got inside the kit. Each pad has a plastic layer covered on the Zelly type gel. You have to remove these plastic stickers while attaching the sensor to the body part. Now let's begin with our project called DIY Electromyography. So here is the connection between Arduino and Myoware muscle sensor. Connect the VCC.
So I'll be stopping the video here, and it's more for you to find out. Thank you very much. If you have any questions, you can reach out to me. And I think now the floor is for the questions.
Thank you very much, Dr. Sanjay. I have noted down a few of the questions raised by the participants. So one has asked, will it be constant reading of the EMG of the muscle? Will this reading will be constant?
Yeah, so as I mentioned during my presentation, this is not constant. It may be depending on different factors. For even sometimes depending on how dry the weather is, because if we are using the wet electrodes, then it also depending on this kind of factors. But of course, the main factors may be the muscle fatigue. Like for example, if you keep this muscle activated for a long time, the muscle activity may go down. So we have seen this in our experiments also, like with the hand rehabilitation robot. So it's not constant.
Thank you, sir. And there is another question. Any recommendations for EMG electrode placement for 5-finger EMG capturing? Is there any recommendation?
So I think the question is like maybe he has some kind of hand prosthetic and he want to activate the 5 fingers. I don't have a recommendation from the top of my head, but it may be a good idea to have a look at the muscle anatomy first. Mainly mainly in the finger anatomy, the muscles are somewhere around the distal forearm. The proximal forearm. So there are tendons driven from these muscles to the finger, and then these fingers are actuated by the tendons. So if you look at some kind of muscles over here, I think it's a good idea. And also it depends on how many number of channels you are expecting to use.
Okay, thank you very much, sir. So that's all the questions that we have.
Great. So thank you very much.
Okay, thank you, Dr. Sanjay Bandaran. Thank you, Kitmi, for going through with that session. And now we'll move on to our next session, which will be done by Dr. Tilina Lalitharatna, who will be talking about brain signal-based control of bionic limbs. So to give a brief introduction to Dr. Tilina Lalitharatna, he's a postdoctoral researcher attached to the Dyson School of Design Engineering at the Imperial College London. He is also a visiting researcher at the University of Cambridge. From 2015 to 2019, he was a senior lecturer in the Department of Mechanical Engineering at the University of Moratuwa. He has published more than 50 peer-reviewed conference and journal papers, and his research interests include human-machine interaction, soft robotics, brain-computer interface, biorobotics, and mechatronics. He is an associate editor of the IEEE SMC 2020 and 2021, and a special issue editor for Frontiers in Neurobiotics, Neurorobotics, and MDPI Electronics. Over to you, Dr. Lalitharatna.
Yeah, can you hear me, Sindhu?
Yeah, you can hear you.
Yeah. So, thank you very much, Sindhu, for the nice introduction. And also, I would like to thank Dr. Sanjay for the nice presentation. Let me share my screen. So, can you see my screen?
Yes, Doctor. We can see your screen.
Yeah, and okay. So first of all, I would like to thank the organizers of this workshop, especially the American Center, together with this Makerspace and the CEBI for inviting me to this workshop. I think this is a really timely and an important workshop, as mentioned by Sanjay, because we saw a lot of tech enthusiastic population in Sri Lanka, like coming during last day and previous session as well. So title of my talk is Move It With Your Mind, Brain Signal-Based Control of Bionic Limbs. Or simply, in this brief presentation, I'm going to talk about how we can use brain signals for control of bionic devices. Before moving to the presentation, to give you a brief introduction about my affiliations and my current work, in MOPLAB at Imperial College London, we try to understand the principles behind real-time conditioning of body to improve the both perception and action, which also involves some brain signal processing. Especially our research focuses on morphological computation, which is a different computation, typical computation in computers, and also embodied intelligence and soft robotics. And in Bio-Inspired Robotics Lab at Cambridge, we focus on investigating bio-inspired robotic system, where how we can understand various biological systems and how we can relate them to develop robots. So this includes, for example, soft robotic based processes, like because we have seen like a lot of processes like Bionics devices from today morning, previous presentation by Dr. Sanjay yesterday as well. So, but mainly most of these existing processes are like rigid processes. But we at Cambridge, we are interested in developing soft material-based processes as well. And then in Bionics lab, during my time at University of Moratuwa, we focused on investigating how we can use brain signals to control assistive devices. So majority of the examples present in this talk are based on studies that we conducted in Bionics lab at University of Moratuwa. So let's move into the main presentation. I think Dr. Sanjay covered some of these parts in his presentation, but I will briefly introduce some of the new terms that I want to discuss in this presentation. So I would like to start my presentation with human central nervous system we call CNS. So CNS is comprised of brain and the spinal cord. The CNS receives sense information from the nervous system and then controls the body response. And in CNS, brain is one of the important part. So human brain is very fascinating and arguably the most complex organ in our human body. So researchers around the world try to understand how the brain works, how the brain processes information, how the brain neural network works to solve complex problems, etc. On the other hand, scientists already have good insight about the structure of the brain and its anatomy. For example, from this figure shows the anatomy of a typical human brain. It consists of different subparts or areas, called cortexes, responsible for different actions. For example, occipital lobe is responsible for vision and object recognition, whereas primary motor cortex, or sometimes called sensory motor cortex, is responsible for initiating body action commands for body movement. And for example, as in this in animation, when a person intends to make a movement, neural signal generated from the brain's motor cortex propagates through spinal cord via motor neurons to muscle fibers, and then it will co-contract the muscles. These neural signals propagate in the form of electrochemical waves, and we call them action potentials. So as action potentials are nothing but electrical impulse, just like EMG. So as Dr. Sanjay correctly mentioned, if we can tap these impulses somehow using an external device, we can use it for various applications, which include control of Bionic devices. So this is where the new term brain-computer interface, or we call simply BCI, comes in. So brain-computer interface is an interface which captures the brain signals using external devices and use those signals to control an external device or an application. There are tons of BCI studies and success stories reported in literature. For example, you can see from this video, left side video, which is one of the most advanced BCI control of an external robotic arm using brain signals. As you can see, the user, or she can fluently control the robotic manipulator using only her thoughts. So which is really fascinating. So she's a disabled person, like as I remember, Bionic disabled person. So as you can see, she's totally she's able to control this manipulator thoughts. And then perhaps this video in right side, perhaps you may have seen this video numerous times. So this is from a very recent video of a monkey playing a computer game using brain, published by Elon Musk's BCI venture called Neuralink.
He's learned to interact with a computer.
This video recently made a huge discussion in
we can interact with the Neuralinks simply by pairing them to an iPhone,
of course, is a
just
tech,
as you might pair your phone
tech genius.
to a Bluetooth speaker.
So at the beginning, you can see monkeys trained to do a task. So in this case, the game. So the monkey is basically trying to control or to play the game using
neurons in this region modulate
one
their
of the limbs,
activity
right?
with intended
So as you can see from this video.
For example, some might become
and
more
then
active when he moves his hand
in the
up,
meantime,
and others when he moves it to the right.
The researchers, they
By
record the
recording
EEG
from many
signals
neurons and
using a
feeding their
wireless system,
activity into a
and then they
decoder
use
algorithm,
that
we are
EEG
able
signals
to
to
predict pages'
train
intended
a machine learning
movements
network, or
in
sometimes
real
you
time.
call it like, let's say, artificial
First,
intelligence,
we calibrate
or
the
you simply call it
decoder by recording
machine
neural
learning. So
activity
machine
as
learning
Pager uses
algorithm
the joystick to move a
basically
cursor to targets
map
presented on the
monkeys'
screen.
thoughts
As he's playing
to the
this
game.
game, we're
And
wirelessly
then
streaming
finally,
in real time the
as you
firing
can see,
rates
you can
from
see
thousands
that
of neurons to the
connection. So
computer.
it's basically wirelessly
Using these
send
data, we
the
calibrate the
signals to
decoder
the
by
computer, and then
mathematically
computer
modeling the
basically train
relationship between
to
patterns
detect
of
this
neural activity and the different
brain
joystick
patterns,
movements
and then
we
it
produce.
basically maps the brain
After
signals
only a
to
few minutes of
the
calibration,
game control
we can
output.
use the output from
And
the
then
decoder to move
once
the cursor
the algorithm
instead of the
trained,
joystick.
you can
Pager
basically
still moves the joystick out of habit, but as
even
you can
remove
see,
the
it's
joystick
unplugged.
or the arm
He's
that
controlling the cursor
the gadget
entirely
that the monkey
with
is holding,
decoded
and
neural
then the
activity.
monkey is able to
Our
basically
goal
control the
is
game or
to
to play
enable a
the
person
game
with paralysis
by its
to use a
brain
computer
signals or by its thoughts.
with their brain
So
activity.
this is really a fascinating
Because they wouldn't be able to move a joystick, they would calibrate
outcome
the
of this
decoder by
BCI in
imagining
recent
hand
past.
movements.
Because one of the important
One of the things the
particular
Neuralinks allow Pager
research
to do
is that
is to play
they
his
managed
favorite video
to
game,
have this
Pong. To control his paddle
sensory
on the right side of the screen,
area or sensory
Pager
basically
simply
make it as
thinks
a
about
wireless
moving
system.
his hand.
But before that,
We've
most of
removed
the
the joystick
existing
altogether.
BCI systems
Now
are
that he's
wired,
up to speed,
as you can see in the other
let's
video.
increase the difficulty and see how well Pager
Yeah,
can
but
play with the Neuralink.
if you closely watch these two videos, you may notice that they had used invasive electrodes for capturing brain signals. Invasive sensors,
As you can
like
see, Pager is
invasive
amazingly
sensors
good
placed
at
on the
mind
brain requires
He's
surgery,
focused,
basically to
and he's
open the
playing
brain,
entirely of his own volition.
and then you have to place that sensor array or the electrode array
It's not
onto the
magic.
brain itself.
The reason Neuralink
So
works
this process is
because it's
complex
recording
and also
decoding
very
electrical
expensive,
signals from the
and also
brain.
with a lot of risk. So,
Great game,
you might
Pager.
wonder, is
And what
there,
better
are there
reward
any
for a
other
monkey
methods that we can use
than a
to capture
banana?
brain signals? Which
We still
might
have
be convenient
challenges
than
spanning
this
many
invasive
fields of
process.
engineering.
So yes, the answer
So
is
if
yes.
you're good at
We have
solving hard
different
problems,
methods of recording EEG signals. So there are various ways of measuring brain signals or looking into brain functionality. I have summarized some of the common methods here. In previous videos, in the two previous videos, researchers have used a method similar to ECOG, where sensors need to be invasively placed on the brain. Even though we can achieve a better detection of brain signals from ECOG, it is often expensive and with potential risk to the user due to invasiveness. And on the other hand, we can use a method called functional fMRI, which is pretty similar to MRI, but it is different in the sense, to detect the brain signals. But fMRI machines are too bulky, and hence they are not really wearable. On the other hand, EEG, or we call it EEG, EEG signals or EEG-based BCI systems is one of the popular methods to acquire a brain signal, because it is non-invasive, wearable, compact size, and reasonably cheap. And of course, there are other methods such as near-infrared spectroscopy, or we simply call NIRS, or MEG, magnetism-based EEG brain signal detection systems. But they have some disadvantages compared to EEG. So EEG has become a good candidate for BCI control in bionic devices such as prosthetics. So because of that, I'm more focusing on EEG-based control of bionic devices in my presentation from now on. There are a number of EEG systems in the market which can be used to measure EEG signals. I have listed some of the EEG systems that we used in the past for capturing brain signals to give you some idea about, for example, market value and then the data you can capture from these systems. NeuroSky, Emotive have very few electrodes, like NeuroSky, as I remember, like 2, Emotive around 14 electrodes. But they are cost in the range of 50,000 to 100,000 rupees, which is compared expensive, I mean, in the sense of Sri Lankan market values. And then there's a one called Open BCI, which is an open source EEG system, which can be used to research as well as hobby applications. On the other hand, there's another system called EGI Density and a GTEC system. So these are high density EEG systems which have a lot of electrodes. For example, EEG system I used in Japan had like 256 electrodes, and we have in Bionics lab at University of Moratuwa, we have a GTEC system which has 64 electrodes. These are really high density EEG systems which have FDA and CE certificates, so that we can use these EEG systems for research as well as clinical studies as well. But one of the most difficult part of these high density EEG system is the cost, because they are pretty expensive. For example, EGI density system that we use in Japan would cost around at that time, like I think like 6 years ago, like around 31 million rupees. And then GTEC system that we have in our lab in Bionics lab was cost around 8 million rupees when the time we purchase it. So you can understand the price factor of this EEG system, because these are like highly advanced system that you can measure very tiny details of brain signals. And then recently, GTEC has introduced another system, which is a cost-effective system called Unicorn Black, which is, I think, a pretty good system because it has a wireless connection, so that you can easily use for research and other or even hobby activities. Yeah. So let's move to the next slide. So EEG signal. So I think Dr. Sanjay discussed about the EMG signals. So I would like to discuss about. I would like to briefly explain about the EEG signal. So EEG signal compared to EMG is pretty small, because EMG signals are in microvolt range, but EMG signals are in millivolt range, but EEG signals are in microvolt range, and also they are not stationary, basically. And EMG can be classified into main classes as alpha, beta, theta, delta, as shown in this figure. So we can use these classes and their behavior to make prediction about the functionality of the brain. For example, whether the person is sleeping, whether the person has any brain damage, for example. We can predict some of these diseases, for example, human behaviors based on EEG as well. But more importantly, there are a few principles that we can use to develop BCIs for controlling bionics. So I have listed some of these commonly used principles here. So the first one of the basic principle that we can use to control bionic device is called SSVP. We call it steady state visual evoked potential. When you look at the blinking stimuli, as in this clip, as in this video, the stimuli will basically generate a SSVP signal in your brain corresponding to that specific frequency. So we can use that response to develop a BCI. For example, if you look at one of these blinking LEDs, the same frequency of signal will be generated in your brain, and we can capture that signals and use that to control a prosthetic device or any other device. And then we have another principle called motor imagery. So when you're imaging a movement, for example, say left hand versus right hand, it will produce a EEG signal. So we call it event-related desynchronization, in simply called ERD, or the sensory motor cortex. So this is basically an amplitude change of the alpha and beta signals. So we call it simply motor imagery. And then researchers have used MI signals or motor imagery signals to design a BCI so that it can be used to control prosthetics. And then there's another brain-related principle called P300, which is P300 is a wave. It is a common principle employed in BCI. So P300 is a wave show a positive deflection EEG signal. So we call it event-related potential, so ERP. So we can use these principles, for example, SCCP P300 or more imagery-based techniques, principles to control Bionics device such as prosthetics or exoskeleton using brain signals. And I think I can skip this slide because I think Dr. Sanjay has mentioned a lot about the signal processing, for example, how you can use EMG to control Bionic device, but I will quickly go through this. So the typical structure of a BCI is shown in this figure. So as you can see, it consists of 3 stages. First stage would be signal processing, and then the second stage would be feature extraction, and then third stage would be signal classification. So as I explained before, EEG is a very tiny signal or very small signal, and therefore it can be easily distorted by other signals. For example, EMG, it can be affected by muscle EMG of your face, and also ECG waves. You can measure your heart waves. So that also affects this EEG because EEG is pretty small compared to those waves. And also other physical issues such as head or motion of your head will add noise to the signal. So therefore, we need to reduce these artifacts by pre-processing the signals at the beginning. And then we can extract different features. So we have mainly 3 different types of features based on their domain. We have time domain, which are temporal features, and then we have frequency domain features, and also we have time frequency domain features as well. So basically, we extract these features, and then we send those features to classification algorithm to really map the raw signals with the required output. So in terms of classification algorithms, as Dr. Sanjay mentioned in his presentation as well, so we have quite a lot of different algorithms we can use to classify these signals. It could be a pretty simple threshold-based classification, but when you have a lot of ED or a lot of sensor signals or a lot of signals from a lot of channels, for example, 250 channels, you cannot simply use simple threshold-based classification. That is where these black box methods, so simply we called machine learning based methods or artificial intelligence, comes in. So you can use those new advances of these machine learning and AI techniques to basically classify these EEG signals and then basically map the EEG raw signals to the required output. Okay, so that's the first part of my research, my presentation. Now I will quickly go through some of the things that we did in Bionics lab at University of Moratuwa related to controls of Bionic devices and with brain signals. So in this study, I'll show you 3 different studies that we conducted in Bionics lab at University of Moratuwa related to EEG and especially BCI. So in this first study, we tried to develop an EMG-EEG controlled prosthetics arm for transradial and transhumeral amputees. We wanted to develop a low-cost, lightweight, customizable prosthetic hand, as most of the existing solutions were pretty expensive with less tech support, especially for countries like developing countries like Sri Lanka. So we designed and developed a 6 degree of freedom prosthetic hand with a weight approximately 430 grams called Pro, just under $1,000 US. So this is the closer look of the developed hand. So we use CNC aluminum parts and 3D printed parts to fabricate the mechanical structure, and then for actuators we use a set of micro GM motors, and all motor drivers and low-level controllers were embedded onto the palm of the prosthetic. So I'm not going to go into more details about mechanical designs this year. And then Pro was able to mimic various hand grips as shown in this video. As shown in this photo. And then at the beginning, we wanted to try control this prosthetic hand using only EMG signals. So we used a pretty simple EMG system called Myoware. So as you can see from this figure as well as video, and then we develop a control architecture for this prosthetic control, as you can see from this diagram. So at the beginning, we train a classifier. We use a backpropagation neural network classifier to basically map the EMG signals with the required portions. And then finally, we use the trained classifier to control the prosthetic hand in real time. So you can see the video. So this is after the training. So I remember I saw one question for the previous session that someone asked, like, where do you place your EMG sensors for detecting these for example. So basically you can place your sensor in your forearm to get those interrelated muscles. Yeah, so I'll quite quickly go to next slide. And then we try to control a transhumeral prosthetic hand with both EMG and EEG signals, because as you may already know, transhumeral amputation means the above elbow amputation, as shown in this figure. So even though we use EMG signals of forearm muscles to control the prosthetic hand in previous case, which is the transradial case, here we can't do that as such, because such amputees doesn't have a forearm part. So to cope with that, we propose a method to control the prosthetic hand. So in this case, Pro, we're using EEG signals. So this is the proposed method. So this figure shows the overview of the control approach. We use a Myoware EMG system to capture the EMG signals of bicep and tricep of the user to control the elbow joint motion or elbow joint motion of the transhumeral processes. And to map the EMG signals to elbow angles, we design a real-time neurophysical classifier, as shown in this simple figure. And in order to control the process's hand, or the Pro, we proposed SSCP-based BCI. So we use an open BCI system to capture the EEG signals of two frontal EEG channels. And then we transform the pre-process time domain EEG signals and frequency domain, and then use a simple threshold-based classification to detect the user intention. So I think you might not understand some of these concepts and algorithms. So perhaps I think I have shared some of the links to the papers, for example, the papers. So you can follow those papers and the research to get more idea about the research. And then this is this video shows the final results of the developed system. So at the beginning, we control the elbow motion using EMG signals, and then before that we use a neurophysical controller. So this is actually after training. You can see the prosthetics closely follow the user's motion intention. And then to control the prosthetic hand, basically we try to control it open and close, let's say. So we simply ask the user to look at this blinking LED. You can see a blinking LED strip around this part of the prosthetic. And then when you look at that, when you stare at that blinking LED, the same frequency of EEG signal generated in the brain, we call it the SSCP, as I mentioned before. So we use that SSCP signals to basically classify the user intention. So basically, the user can just look at these LED strips, and we can control the hand open and close. Okay, so let me move to my second study that I want to discuss here. So as I said in the beginning, so we can use BCIs for controlling other assistive devices such as meal assisted robots in this study, because this may be not directly relevant to Bionics Limbs, but I thought of briefly present this to explain the different application of BCI, because this same concept can be easily translate or extend to Bionic control as well. So in this project, we aim to develop a meal assistant robot for patients suffering from complications such as spinal cord injuries or SCI injuries or ALS. The proposed system has 4 degree of freedom robotic arm with a spoon to feed the user and a miniature camera to detect the user mouth position and open and close. And then we use an open BCI system to capture the user intention via EEG. The developed system is shown in this figure, and we place 3 containers in front of the stores. We place 3 containers in front of the users to store the different dry foods. And then to control this meal assistant robot, we use a 3-stage approach. So in the first stage, we use EEG-based intention detection system to detect the desired food of the user. So for that, like we simply place 3 blinking LED panels in front of the user, and then we ask the user to stare or look at the particular LED panel to basically select the food that he wants to eat. And then SSP signals generated from the brain. So as you can see from these 3 plots, so while he was looking at 6 Hertz, 7 Hertz, and 7 Hertz and 8 Hertz. So same frequency can be detected from the brain, and then we use that to classify the user intention. And then at stage 2 and 3, we use a miniature camera to track the mouth position, mouth open, close, to basically feed the food to the user. So this video shows the results. So yeah, so basically, if you want to use this system, so you have to stare at one of these LED panels, and then within a matter of seconds, so as I remember, around 10 seconds, the algorithm is able to detect the brain signals, and then it will basically send the signals to the robot. And then the later stage, it uses vision-based algorithm to detect the mouth position as well as with the inputs for the person is open mouth or not, and then based on that, basically feeding the food. Yeah. Okay. So quickly move to my final example. This is also not directly relevant to Bionics, but it's still it is an assistive approach for differentiable community, and the same technologies can be extended to design and control Bionics teams as well. So in this study, we attempted to develop a wheelchair with a robotic manipulator to assist population who are suffering from complications such as Lock-in syndromes or Bionic paralysis, such as in this figure, probably you know this person, Stephen Hawkins, a very famous scientist. So the overview of the proposed approach is shown in this figure. For example, so in this study, we design a motor imagery-based BCI to detect the user intention. So as I mentioned in the beginning, MI signals are generated when a person do a movement or trying to do a movement or just think of a movement. So for example, if we can use EEG MI signals to distinguish whether you are moving your right hand versus left hand, or maybe your right foot versus left foot, or right foot versus right arm, for example. So we use that principles of motor imagery to control this wheelchair as well as the robotic manipulator itself. So our proposed algorithm consists of signal pre-processing and then feature extraction to detect the motor imagery signals. But I must tell you that these motor imagery signals are pretty difficult to visible in raw EEG signals, just not like SSVP as we used in previous studies. Therefore, it was a really challenge to detect these signals. So for that, like we had to use a machine learning technique, bit of advanced machine learning techniques. So we use multi-layer perceptron neural network, kind of a with, as I remember, with a lot of nodes. And then we use that to basically train the algorithm, and then to detect the EEG signals when a person imaging a left hand motion versus right hand motion. And then finally, we use that classification, classifier to basically control the wheelchair and the robot, the manipulator. So you can see the complete video of this process. So let me play the video. So at the beginning, we place the electrode cap on the user, and then next step was to train the MLP, or multi-layer perceptron neural network classifier, to basically to detect the motor imagery signal. So this is the training phase. So we showed some messages, for example, rest, left versus right. So when you see the left, so basically we asked the participant to basically lift his left hand, as you can see from this video, and the right, when he sees right, so basically he has to raise his right hand, and then basically train the whole neural network. And then after that, I think we had to train the algorithm for like almost 2 months, as well as I said, motor imagery signals are base BCS are pretty difficult to train, and it takes a lot of time to train. For example, not only the algorithm, but also person who using it must be trained to emit these EEG signals. So we had to train him for like 2 months, as I remember, at least 1.5 months to get these required output. And then, but finally, he managed to control the wheelchair as well as the robotic manipulator based on his thoughts. So we in addition we made a GUI, graphical user interface, so that we can basically enhance this EEG based classification to do different activities. Because what we basically classify, that we try to classify in this experiment, in this study, was left versus right, left hand motion, imagined motion versus right hand imagined motion. So, but you can see like we can control different motions of the robot manipulator as well as wheelchair. So which needs a lot of inputs, but to avoid that lot of inputs from the controller, we use a GUI. So basically, user can control the GUI using stores, and then we transfer that GUI signals to control the robot at the end and the wheelchair. So I think, yeah, there's another resting clip maybe after this. So yeah, so he managed to control the wheelchair in different directions using GUI, but GUI is basically controlled using brain signals. So as you can see, I mean, it was not that speed. We couldn't make it to a really high speed because, of course, it takes time to really classify these signals. And then in this particular video, you can see how he managed to control the robotic manipulator to pick and place tasks, for example. So he managed to basically control the robotic manipulator to pick an object and then place it in a given position, purely based on thoughts. Yeah. Okay. Yeah. So that's it. So this is my final slide. So as you can see, BCA and Bionics are very exciting field of research as well as industry, which have a lot of potential for further improvements. As for the future direction, I can think of, I would love to see new sensor technologies detecting brain signals, especially new sensor detection to make dry electrodes and also bio-compatible electrodes for implanted electrodes. For example, if we are going for invasive type brain sensors, and also wireless technologies, wireless sensor technology will be really helpful to improve the BCI field. And also, of course, as similar to other fields, machine learning techniques and AI techniques, artificial intelligence techniques can play a huge role in enhancing the accuracy of BCS as well as reducing training time. Because, of course, at the moment, for example, in the previous video, it took around like approximately 1.5 months, 2 months to train that whole algorithm as well as the person. So if we have improved version of machine learning techniques, we could have easily reduced this training time of these BCIs. And also the other important thing is that looping back the multimodal feedback, for example, vision and haptic, because in real life, not only we control the limbs and body parts of our body, but also we can sense different sensation. For example, we can we can feel using haptic feedback. So we need to incorporate this feedback to our BCI and then finally to Bionics to really give the feeling of real limbs when we really when we really introducing processes for these differentiable committees. And then finally, of course, we need to think about the adaptability or the conformability of BCIs to the users for long-term use of these processes, because at the moment, majority of these processes are in research level. So especially the brain-related processes. So we should find better ways to really make these systems more comfortable as well as for long-term use, so that people can, the needy people can use these systems in their activities of daily living. Yeah, I think that's all for my presentation. And if you have any questions, you can ask in next session. And thank you very much. And if you have any question, any personal questions, you can directly send to my email as well.
Thank you very much, sir. I have noted down one question from the participants. One have asked, are there any possibilities to access the neural network which is essentially carrying the signals to the muscles instead of the muscle itself?
Can you repeat the question again?
Are there possibilities to access the neural network which is essentially carrying the signals to the muscles instead of the muscle itself? I think they mean about intercepting the signal before going it into the muscle.
Yeah, so that is what happened in BCI. So as even if you can remember, even in Dr. Sanjay's presentation, so we have different levels of I mean, in the neural CSN, so central nervous system, we can tap these signals in a different location. For example, from the brain itself, and then in EEG, in case of EEG, we record it from the scalp, and also we can tap those signals from the muscle as well. So as far as if we can capture these signals from the very beginning, where the signal initiates, so that is good, because that is where the signal originates. So that's I think my answer would be like, yes, of course we can do that, but yeah, it's challenging.
Yeah. Thank you very much, sir. So that's all we have questions, because most of the questions were answered within the chat. So thank you very much for the nice presentation.
Yeah, thank you, Gizmi. Thanks.
Pasindu, you are on mute.
Yeah, you are muted, person.
Sorry, my bad. So once again, thank you, Dr. Lazaratna, for that amazing and truly enlightening session. So now we'll be moving on to our next session, which is a bit different. It is about, we will have two people sharing their experiences regarding the development of prototypes for bionic limbs. So first off, we have engineer Achinta Abesiri. So engineer Achinta Abesiri received his BSc from the in engineering in 2016 and his MSc in mechanical engineering in 2019 from the University of Moratuwa. He pursued his MPhil degree in electrical engineering at the University of Moratuwa, and it is to be conferred in 2021. Currently, he is pursuing his PhD in Computer Information Sciences at the College of Computing and Digital Media, DePaul University, Chicago, Illinois, in the USA. He was previously a temporary instructor at the Department of Mechanical Engineering, University of Moratuwa, and a research scholar at the Center for Advanced Robotics at the University of Moratuwa as well. He is an associate member of the Institute of Engineers Sri Lanka and a graduate student member of IEEE. His research interests include assistive robotics and social robotics. Then we have engineer Kitmi Vidanage, who you already know, who has been moderating our Q&A sessions. So engineer Kitmi Vidanage received her PSc in engineering, in mechanical engineering actually, from the University of Moratuwa in 2019. She served as an instructor and a junior lecturer in the Department of Engineering at the University of Moratuwa, and from 2019 to 2021. Currently, she is a research scholar attached to the Bionics laboratory at the Department of Mechanical Engineering in University of Moratuwa. She is experienced in designing and developing robotic prosthetic devices. Her current research areas include occupational exoskeletons and developing biomechanical systems focusing on the circular external fixators. She is an associate member of IMEC-E and a student member of IESL. She is also experienced in teaching biomedical engineering technology to undergraduate students. She has authored several research publications related to biomedical devices. So this session is going to be truly a wonderful one, and I hope that everyone will enjoy. And now over to you, Mr. Achinta.
Thank you, Pasindu. So let me share my screen. Can everybody hear me?
Yes, you are loud and clear.
So thank you, Mr. Pasindu, for the nice introduction. So I am Achinta Abesiri. So today I'm going to talk about my final year research project, which was done back in 2016. So it was about development of a 5-degree of transhuman processes. So this is a video that was published and also for telecasted in numerous platforms. This is regarding our research. So now you know what we are going to talk about today. So that was my final year research project, and this is the team that was there to build that robotic prosthetic device. So first off, Professor Rohan Gopura, he was the principal investigator of that project, and also Dr. Kanishka Madhusankar. Unfortunately, he's passed away right now. So he was our co-supervisor, and also Dr. Sanjay Bandar was an external collaborator for that project also. So our student team consisted of 3 members. So myself, Nirupa Arachige, and Taridu Silva. So what happened when we started this project? So basically, we approached Professor Gopura regarding this project, but first off, we had lots of questions like, do we have the required skill set? Do I have the required knowledge? Is the time period is enough to complete this work? So Professor Gopura gave us a simple answer. So now you are seeing an aeroplane. So it has an interesting story because it inspired our whole research. Because he said, so if you have the required skill, required enthusiasm, and also the courage to complete the work, you will be able to build even aeroplanes. So that was huge motivator for us. So that's how we begin our final year research project. Then we had to analyze what we are good at, what we know, what we don't know, what we can't do, and also what can we do to improve ourselves, and what are the sources available for that. And also funding was another threat that we had to go through, and also the expectations of the society is very high. So battles were within ourselves because we were a fresh team, and we don't know what are the capabilities of each other, and also we don't know what we are good at back at that time. So it took several months for us to get into line, and we discovered that for myself, I'm good at design, and Mr. Tariq Silva was good at manufacturing, and also Nilupa Harachige was very good at controlling. So after that part is done, we had to set up goals. So goals were setting up goals were another challenge, because we have to set up goals that could be achieved within the time period we were given, and also we had to know that we are not going to make a bionic arm that is more like the Bionic arm. So it would be a very ugly one, but it should be able to do the work as we intended to. So this is some 3D models and also some motion analysis done in the design phase. After design phase, we manufactured the items. So all the manufactured items were put together or assembled by ourselves, and all the screws and nuts were tightened by ourselves. So it was a very challenging experience for us, and also it was very fun. As mechanical engineer, we don't get much of those experiences in the university period, but it was very fun, and it was very fruitful for us as mechanical engineers too. So this is a video we taken in the control design phase. As you can see, the arm is not moving as the signal comes from the biceps and tricep muscles. So basically, in this project, this is a transhuman prosthetic device where the amputation is done between the elbow and the shoulder. So basically, we don't have much of the muscles in order to extract the muscle signals. So what we did was we acquired the muscle signals from biceps and triceps and used it to successfully do the flexion extension motion. Once it was done, we shifted those motion. We shifted that motion sequence using motion algorithm, sequence of motion algorithm. And finally, we were able to control our prosthetic with that algorithm, and he also used the task switcher. So as you would have seen that in that video. So once the controlling phase was done, basically our prosthetic was in a good phase where we can evaluate for its performance. So the first experiment we done was to reach out to an object and pick it and place it. So those are the results we observed, and also we checked the motor performances and in the acceptable parameters also. And you can see there's a motion comparison between human limb and also the prosthetic arm that is mobile, that is the arm we manufactured. And as you can see, they are also very close to the human upper limb parameters as well. So if you need more details regarding this project, there's a conference paper published in ICOR, International Conference on Rehabilitation Robotics, that was happened in 2017. So this research paper is available for you to read. So reach out to that and explore more about this project. So I'm not going to say anything about this video. Just look at it and see what's happening there. So after that video, I will talk about that. So what we are doing here, we are measuring the joint angle of elbow, and also we are taking the EMG signals at the same time, and we are trying to build a relationship between the angle and the EMG signal. So you could say it's pretty cool and nerdy, but we worked on this concept for almost like a month, only to find that there's no relationship between the EMG signal and the joint angle. So you could say it was a waste of time, but the things we learned during that time is very fruitful for our success in our research, because even so, it's basically tempting to think that there could be a relationship between EMG signal and the arm, or EMG signal and the joint angle. So we had to test it. So even though we had some doubt, we tested it. So we found out that there's no relationship between those two. So it took pretty much a month in order to get that result. So after successfully evaluating the performance of the processes, we get national level recognition in a high level, actually. For as you can see, we were on the digital media, and also we were on the printed media. So we had several interviews with the TV channels, and also our project was published in many other newspapers as well. So if I talk about the international recognition we got for our research, we were able to publish in this project in Rehab Week 2017, that was held in United Kingdom back in 2017. So as a final note, I would like to say it all begins with an ambitious thought. So we all want to make a prosthetic arm that is more like the human arm, but it's not the reality. You won't be able to build a robotic arm that is more like the human arm overnight. So it takes a lot of time, but you have to adjust your goals accordingly within the time parameters. You have to adjust yourselves as well, and never get discouraged by the factors like lack of knowledge, experience, and etc. For example, so I was the one with the academic lowest academic rankings. So even now I am doing the PhD. So before this, I did a master's degree in mechanical engineering, and also I did a electrical engineering master of philosophy degree. So it didn't matter, but what this project did to me was that it encouraged me to explore more, and also it gave me the strength to look for new avenues, and basically it inspired me to be a great researcher in the future. So I showed you a small video where we wasted our time on the things that is not there. So if you are not sure about something, you have your peer colleagues, and also you have your supervisors. You could ask for help, and you shall get the help. So it may save you a lot of time rather than wasting your time. So be a team player, because this kind of project, you can't build it by yourselves. You need the assistance of other peers as well. So you have to be a team player. You have to respect their ideas, and also you have to argue, and you have to adjust your ideas with the others as well. And the main thing in this kind of project is that you have to enjoy the work as much as you can. It could be tiresome, but the results can fulfill your life in the ways you couldn't even imagine. So it was a memorable experience for me. So this kind of project could make a memorable experience for yourselves as well. So that's it about my presentation, and those are about my experience as undergraduate in Department of Mechanical Engineering, and this was about my final year research project. So if you have any questions, you could reach out to me. My email address is there. So, and also if you have interest in looking into our research project, it is published in ICOR 2017, and the publication details go there. So just type mobile and you will get lots of information about our research project. So thank you. And once again, I would like to thank American Center for inviting myself to conduct this speech. And also I would like to thank all the organizers and participants who gave me this chance to speak out myself about my experience. Thank you.
Yeah, thank you, Mr. Achintavesiri. That was a truly eye-opening one, and that would have helped a lot of people, a lot of the attendees who are looking to get into this line of work as well. So thank you very much. So now we'll move on to Engineer Kitni Danage to share with us her experiences in this line of work. So over to you, Kitni.
Thank you very much, Mr. Pasandu, and thank you for the nice introduction that you provided at the beginning of the session. I'm going to share my experience. Okay, I hope you all can see the screen now.
Yeah, we can see a screen.
Okay, thank you. So, hi, I'm Kitmi Vidanage, and I'm here to share my story, our story about developing a bionic limb. Our bionic limb was called Trophy, which is transtibial robotic prosthesis with the hybrid powering mechanism. And this is actually our undergraduate project, so finally undergraduate project. And what is Trophy? Actually, Trophy is a prosthetic ankle foot device. It is designed for people with transtibial amputations, and we designed Trophy so that it has hybrid powered actuation. That means it is powered both by body power and by using an external power source. And we used a dual spring system in here, and we had a spring locking mechanism. And we use this device to harvest body energy and reuse it when walking. And this prosthetic unit can mimic natural kinematics of the ankle joint. And this is our team. Actually, our main supervisor was Professor Ruwan Gopra, and our co-supervisor was Engineer Pubudira Navira. And under their guidance, we three of us got together, and especially Engineer Prasita Satsara and Engineer Esni Lakshman. Those were my colleagues who got together with me in developing this device. And when we talk about the recognition behind our design, actually, we could publish a conference paper in Moratuwa Engineering Research Conference in 2019 based on this research. And also we were able to win the best paper award at that same conference for this device, for this research. And we also used this device to educate general public regarding the robotic prosthetic devices, especially at exhibition called Shilpa Sena, and also in an educational program that was conducted in Takshila Mahavidyalaya in Mahavidyalaya. In both those occasions, we used this device to give general public an idea about prosthetic devices and how we can make a difference as engineers. So moving on, yes. So when you think about our design, we actually this is a large project. We were engaged in this project throughout the year, but we can basically divide what we did into 4 basic steps. We identified the biological requirements, we designed and developed the mechanism, we design and develop the control system, and finally we test the device for performance. So this is the basic steps in designing any prosthetic device, but the most difficult and the most time consuming step is the first step. So the reason for that is we are actually, I was a mechanical engineering undergraduate, so my background is in that side. I'm not educated on biology after my O-levels. So when I got into this project, I didn't have a clear idea, as engineer Achinta said. It was very challenging, but we studied and we got to know more information. We read many things, and we tried to understand the biological requirements behind the design of a prosthetic. And after that, we could move forward in developing this device. So in the first few months, actually what we did basically was reading more and more about biological concepts and medical concepts related to this prosthetic device. So let me explain. So when we developed our device, we actually we are developing an ankle prosthetic device. So we have to observe what happens in a real ankle. So if you look at this device, look at this image right on the left side, you can see this is natural ankle joint. And in the natural ankle joint, there are 3 degrees of freedom. One is inversion and eversion motion, and the other one is plantarflexion and dorsiflexion motion, and the other one is the internal and external rotation motions. So when we design our project, one thing we understood is that if we are going, the basic requirement in our design is walking. We first tried to develop a device which can use for walking. So when we think about walking, the basic movement that we need is actually plantar and dorsiflexion movements. So we decided to use that motion in our device, and also to allow to walk in any uneven terrains, we had to allow eversion and inversion motion as a passive method. So we didn't implement internal rotation and external rotation in our device, because that motion can basically be adapted from the hip joint, and if we try to incorporate all the things at once, it might be a complicated device with a lot of power requirements and lot of weight. So first we needed to prove the concept of this device, so that we try to simplify it by identifying that the main requirements are these 2 degrees of freedom. And then as I told you before, we had to read a lot. So when reading about biomechanics and walking gait, we identified that there are actually, as Engineer Pupudu Pranavira said yesterday, maybe you can remember, we have 2 main phases in walking: stance phase and swing phase. Stance phase is when the foot is on the ground, and swing phase is when the foot is moving through the air. So the stance phase can be divided into 3 subphases, like controlled plantar flexion, controlled dorsiflexion, and powered plantar flexion. And actually, this controlled plantar flexion is when you put the heel on the ground at first, and after that, when you put your toes on the ground, then that phase is the controlled plantar flexion. After that, from that position until you take the heel off the ground, that phase is called the controlled dorsiflexion. And after that, when you push with your toe, push with your ankle to move your body forward, that phase is called the powered plantar flexion. And we identified that in actual scenario, only the powered plantar flexion is the phase that the body is provided a boost. The ankle is actively providing a boost to move the body forward. And during the controlled plantar flexion and controlled dorsiflexion, we are not actually doing any, the ankle joint is not actually doing any positive work. It's just trying to control the movement of the joint rather than trying to move the body forward. So after we identified that, we realized that these 2 phases can be controlled by a passive method, like by using a spring, and this phase we need an external power source. So we decided to use a hybrid mechanism where part of the working cycle is passively controlled and the other part is actively controlled. And we decided to use energy stored in this controlled dorsiflexion phase to power the powered plantar flexion phase together with the motor power. So basically, we use a hybrid powering mechanism where we can harness the body energy in addition to the power provided by the motor. So in our design, actually we basically use this graph to get the basic idea for the design. So if you look at this graph, this is based on the ankle torque and ankle angle, and this shows the gait cycle of a person. And when I was talking about the subphases like controlled plantar flexion, controlled dorsiflexion, you can see this part is the controlled plantar flexion phase, this part is the controlled dorsiflexion phase, and this is powered plantar flexion phase. So when we think about different phases, I told you that we are going to power this phase using the motor, but these 2 phases should be controlled using the, we decided to use control them using the torsional springs. So when you look at this diagram, you can see the slope of this graph are slightly different. So we understood that by looking at this graph, the stiffness of the ankle when we walk differs, right? The stiffness of your ankle differs depending on the phase on which you are in when walking. So based on that, we decided that we need 2 different springs with 2 different stiffness values to control the ankle. So that is how our thought process went. We first observed what happens in the real leg, what happens when we walk. We try to identify the key features in walking, and then based on that key features, we try to develop our requirements. So based on the things that I explained in the previous slide, we require 2 subfaces of the gate controlled by springs, and these 2 springs should have 2 different stiffnesses, and the other face can be controlled by the motor. So that is the requirement. So based on that requirement, we developed a special mechanism. So here we have plantar flexion spring, and here we have dorsiflexion spring, and we developed a special mechanism to select between these 2 springs. So this is this mechanism is actually cam pin is moving along a cam guide. That kind of a mechanism. That mechanism use one-way bearing. I'll explain what it is. That mechanism can be used to differentiate between the 2 springs. So that is how our thought process went. That was the most important aspect in our project. And until we identified that requirement, we couldn't move forward. So until we identified that requirement, we were just like walking in the dark. But after we identified what are the requirements and how to achieve that through a design, once we came up with the solution, then everything moved forward with a good speed. So I'll move forward. So as I told you, that device, that design didn't come to that phase at once. We first, after identifying the requirements, we came up with different design solutions, like to lock the springs. We tried to use several mechanisms such as ratchet wheels, then a vernier lock, and we understood that to use these kinds of mechanisms, we need maybe an electromechanical system, maybe something like a servo motor or something to actuate the lock. So, but we thought that it might be problematic, and then after some time, after some evaluations on our designs, we came up with a design that I showed you. The design was using a one-way bearing, and that locking mechanism was a fully mechanical system. So that was the turning moment in our project, and after that we could design this we design and develop this device. Yes, so actually this is our final design. You can see the design. We have the locking mechanisms, and here we have the one spring, plantar flexion spring, and we have dorsiflexion spring here. And this is how our device works when we actuate it with the motor. So we have used the motor over here, and actually you can see here there's the animation that is shown here is made using SolidWorks. So we actually got a lot of use by using SolidWorks to get a graphical representation of our design. Before going into actual actual fabrication, we used a graphical representation of our design to get an understanding about the improvements that needs to be made and any other changes that we need to do. And when we think about the fabrication, actually we used several fabrication methods. Basically, the thing we use most is CNC machining, and we use some 3D printing to fabricate this part, the cam guide part. And we have some ready-made components like foot component, we purchased it, and also the one-way bearing was purchased. And I have to make a small clarification about one-way bearing. It is actually a bearing that can rotate only in one direction. When it tries to rotate in the opposite direction, it locks. So it is a crucial element in our device, and we use that as well. So it was a ready-made. We purchased it off the shelf, and we had made some manual springs using some local manufacturers. We calculated the stiffness that we need to have in those two springs using the data that we have, the biological data. And after that, we prepared the specification of the springs that we need, and we provided them to a local manufacturer and got them manufactured. And after that, in manual machining, we use some manual machining methods for that as well. So these are the fabrication methods that we used in our project. And actually, apart from the off-the-shelf components, all the other components were developed within the university with the facilities that we have, like we have as Professor Wan Gokuran, Engineer Pudrani said yesterday, we have many facilities within the university like Dye and Mold Center and machine shops and all those things. So we developed, we manufactured most of the parts within the university, and we did some weight optimization. Weight optimization is an important aspect when we think about the prosthetic devices, because actually when someone is using a prosthetic device, they need to have a reduced burden. When the prosthetic device is heavy, then it will be an added burden for the amputee. So we have to reduce the weight of the device as much as possible. So it is true that this is a prototype, but we needed to reduce the weight of the device as much as possible when we prepare the prototype as well. So we used some topology optimization methods. That means we started from a structure like this. For the external structure of the device, we started from a structure like this, and we provided some, we simulated this structure on software like ANSYS, and then we provided some dynamic load for the structure, and then we identified which what are the stress distributions in this structure, and depending on that, we identified which parts can be safely removed without making the device vulnerable. So after that, that is how we came up with this structure, and after that, we could reduce the weight up to 1.4 kilograms. And actually, the human foot alone approximately weighs about 1 kilogram. So we decided that it is a reasonable value for our design. Of course, we can improve this weight requirements. I mean, we can make it more lighter by using different kind of materials. Of course, this is the first prototype. And then this is a brief idea about the working principle of the design. Actually, as I told you before, we had control plant flexion. In that phase, this plant flexion spring is loaded, and in the controlled dorsiflexion phase, this spring is unloaded, but the other spring is loaded. And in the powered plant flexion phase, this energy absorbed by this dorsiflexion spring is used to support the motion, and also additionally we support that motion by the motor as well. So in the swing phase, again the motor resets the position of the leg, the position of the ankle. So we used a physical human robot interaction control system That means we didn't use any biosignals. We used actually physical signals like here we use force sensitive resistors to identify the gate phase. So we fixed two sensors, one here below the toe and one here below the heel, to identify whether the whether the heel or the toe has been touched the ground. And based on that, we identify the gate phase. And depending on the gate phase, we provided the velocity profile to the device to actuate the device. So we didn't test this prototype device on an actual amputee because we needed to confirm the operation. So we fixed it in parallel to a healthy person's leg by using a specially made test rig. So I'll show you a small. So this is how our results came up. You can see this device can mimic the actual leg motions in all the phases. So I'll show you a small video. So you can see how it can move parallel to the actual leg. So we can prove that we could prove that this device can work mimicking the actual leg motions, actual ankle motions when moving. So this is some results that we got. Actually, we have proved that the natural ankle motion, which is shown in the blue color line, is closely followed by our bionic ankle motion, which is shown as the orange color line. So we have a 97% correlation between the two data sets. So the main challenges that we faced, as I told you in the beginning, the main thing is familiarization with the medical related terms and concepts. We needed to read about the biomechanics, the anatomy and physiology of the ankle. And after that only we could move forward with the project. So since we were not familiar with that subject, we needed to read a lot and get a better idea about the subject. And also another problem was acquiring electronic components in Sri Lanka. We had to go for international market. We had to ship some components from the international market because we were unable to find some components in Sri Lanka. So it is a common problem that we have when developing devices in Sri Lanka. But with today's technology, it is actually it's actually not that much of a problem because we can reach to international market in case we don't have the required things. And that's about it. I hope that our project gave you some idea about what goes behind the developing of a prosthetic and how your thought process should be when you try to design a prosthetic device, because mainly our focus was on the biological requirements of the ankle, and based on that only we move forward. So if you want to read more about our research, you can go to this link, and also you can contact me using this email address. So thank you very much. And if you have any questions, you can please ask us. And I have seen that some questions that we have. Okay. One question is for Engineer Achinta. How did you coordinate the functions of elbow and the fingers by the muscles if both were done simultaneously?
Yeah, that's a pretty good question. But the thing is, in our algorithm, we didn't incorporate such kind of algorithm to control both elbow and the finger simultaneously. Instead, what we did was, since there were limited muscles available in order to extract the EMG signals, what we did was we sequentially activated all those motions, and finger motions are done in the fifth motion sequence in our EMG based algorithm. So it could be done, but in our case, we didn't do that because it was not our priority. Our priority was to design and fabricate a high degree of freedom transhuman processes, and we done that. And also we were able to control that. So we didn't look into that, but there are ongoing researchers that have that capability to control both elbow and also the fingers.
Okay, thank you. So I have a question. I think it was directed to me. It asks how much residual limb can be accommodated with trophy design. So actually, when we design our device, we developed it for a person of 50th percentile. That means average male person. And then when we design the device, we actually targeted for a 30% of the residual limb. So 30% residual limb. So that I think that answers your question. And of course, we have to change this. I mean, if we are going to use this for an actual amputee, we have to think about the amputee status, and we might have to make some modifications. So that's the answer for your question. So this was a first prototype. We assumed that the amputee is going to be a person with 30% residual limb, and based on that, we conducted our research. So when I say residual limb, I'm meaning about the length of the shank. And yes, I think that answers your question. And also there's another question: has trophy been tested, designed for activities like hiking? Is it safe of such things? Because hiking uses more degrees when hiking more than walking. So yeah, that we have not tested trophy for hiking. We actually right now in this version of the device, we only developed this for walking, because I'm sure that when we use other devices, when we use it to other activities, we need to have different ranges of motion, and we need to take into consideration special circumstances. Like when we are using it for hiking, we also have to think about the robustness of the design, and we also have to think about the such special requirements are there, and we have to make special considerations when we think about such designs. And right now, trophy is not designed for such activities. We specifically limited our scope to walking because one thing is this was an undergraduate project, so we had to limit the scope. And the other thing is actually this is the first version, so we can develop it in the future to accommodate more types of things. And Engineer Achinta, we have questions. I think it is directed to us both. What is the advantage of this mechanical system over electropneumatics? Yeah, maybe it was directed to me, I think. Right. So please let us know if it is directed to Engineer Achinta. I think when we talk about trophy, yeah, when we think about trophy, when we think about, I mean, I think you are referring to the place that where I talked about the mechanical locking system in the springs rather than using electromechanical system. So basically the consideration for us was that when we use additional electronic parts or electronic parts, we need to go for additional power sources, or we might need to go for that's the basic requirement, because when we propel our body forward, we need to have a high power. So if we are trying to get some if we are trying to get some additional components like electropneumatics, one thing is that it increases the weight of the system. The other thing is that we need more power sources, and of course in the end the consideration was that it increases the weight requirements. So we have to reduce the weight. And also when we think about fully mechanical systems, we can by mechanical means we can make it more reliable. So that is another consideration that we had to think about. So I think that's all the questions that we have. I'm sorry if I missed any questions. So that's all I can see for now. So thank you very much for providing us this opportunity to share our experience in developing bionic devices.
Okay, once again, thank you, Engineer Achinta Abesiri and Engineer Kitmi Vidanage for your brilliant insights. So now we move on to our next item on our agenda. I would like to invite Professor Ruwan Gopura, who's the director for research at the University of Moratuwa and also the head of department in the Department of Medical Technology, University of Moratuwa, to give us his closing remarks of the workshop. Over to you, Professor Gopura.
Right. Thank you, Pasindu. Right. Anyway, so host has stopped my video. Okay, but without video, I'll give the concluding remarks. Right. First of all, I would like to thank the American Center and American Embassy for giving us this opportunity to conduct this Bionics workshop for tech enthusiastic people. Of course, as a country, as a nation, we know that for the development of the country, we have to study and we have to follow the STEM education, especially science and technology. So during these 2 days, 4 hours, weekend evenings, we took your time, and we believe that we delivered you a good knowledge and our experience. And we believe that we had a good as well as fruitful workshop. We always try to give the knowledge for different level of audience. And we included experiences of our previous students. And during the 2 days, 4 hours, first we tried to give you a brief introduction about Bionics Limbs, why we need Bionic devices, and what are the Bionics and what are the Bionic devices, and their usages. And then we move to from need to aid, the design process of the Bionics Limbs and design consideration, how we start the design. In order to design these systems, we need to know about the biology as well as engineering principles, mechanical engineering, electrical engineering, and some other related engineering knowledge to develop these systems. And today we discuss about muscles for communication, muscle signal-based control of bionic devices. Dr. Sanjay briefly but nicely explained about controlling of this device using electromyography signal. Right, thank you. Now I'm on video. Right, and then Dr. Thilina explained about move it with your mind, how brain signal, especially EEG signal, can be used to control the bionic limbs. And then at the end, our success stories, Engineer Achinta and Engineer Kitmi, our former student at the Bionics laboratory, explain how they developed prototypes of 2 Bionics limbs. So we hope that during 2 days, 4 hours, we delivered a fruitful knowledge as well as our experiences. And I also would like to remind you again about the challenge. Remember about the design challenge. You have to design a prosthetic device. So from designing, from gaining the designing experience from these devices, you can learn a lot. When you design, probably you have to study about the biology as well as some engineering principles, as well as you have to select some, if you do a proper design, you have to select some devices, actuators and sensors, and you have to study about the controlling systems. So try to do the design of the finger. Even if you are not participating for the challenge, you can try to design the system. And also, we always, as Bionics Labs, as well as the Center for Biomedical Innovation, we always like to share the experience and the knowledge that we have gained from our work, especially from our research. You know, the difference between probably the difference between the school, the teacher and the university lecturer is creation of new knowledge. That is the research. As the university community, we are carrying out research in Bionics Limbs. We always try to share our knowledge. Of course, we have done some work to share our knowledge, especially in school level. There are science exhibitions as well as technological exhibitions. But we would like to continue it in more like more greater scale. So if you have anything, please contact us. I'll share our contact details. I have shared my personal emails yesterday, and if you want anything, you can contact us using these two emails as well as our personal emails. And also you can go to Bionics Lab and the Center for Biomedical Innovation web pages as well. So thank you once again. Thank you very much, especially the American Center and US Embassy, and Sanjay Dushant, Ranjan Kulatunga, Nadi Prajnaratna, and our team at the Bionics Laboratory, and all the participants. Thank you very much.
Thank you very much, Professor Gopura. And yeah, so to close out this workshop, I would once again like to remind everyone, there have been, we have posted the links for a feedback form. Your feedback will be very valuable to us, so we can perfect this concept of workshops going forward. And again, I would like to remind everyone about the design challenge that Professor Gopur also talked about. This PDF has been shared in the chat as well. And I would once again like to remind everyone that for everyone, if you have been chosen as a winner, you will get an educational kit, the Inspire 1.0 educational kit. And so please, everyone, go through the PDF, and I encourage everyone to have a go at this, take on the challenge, and go ahead with it. And once again, our contact details has also been uploaded in the chat. And as Professor Gopura kindly shared with everyone, you can find us at the following, as it's been shared on the screen. Through the following platforms, you can reach the Bionics Lab and CEBI as well, for if you are interested. And then to conclude, I would first of all like to thank the American Center for organizing this, providing the platform to connect experienced personnel in the field and enthusiasts to keep this field of work going forward. The Makerspace team for the coordination they have done. The Bionics Lab for providing all the resources to make this workshop a success, and the coordinators at CEBI as well. So I would once again, last but not least, would like to thank all the attendees as well for giving us your time, especially on a weekend, 2 days. And I hope that this workshop has motivated you to keep going and to make to create new things in the field of bionics. And I would like to thank you for your participation. Thank you very much.